And then you guys know how to derive mean and also how to derive variance. So at this, you should understand how to derive these. And how about mode? Here we have the same level, so we don't have the mode. And how about maximal likelihood? Later in the remaining discussion, we will already know how to have a MLE, but at this moment, A hat means the estimation for A. B hat means the estimation for B. Because A and B are the two endpoints. So we can use the feature for the two endpoints if we don't care about MLE, how to derive MLE. So how to find A, the minimum among the observations and the maximum among the observations, and so that we can set the two values to the endpoints A and B. All right, so using the way you can understand, but in fact it says this one follows the MLE, the maximum likelihood estimate. So how to have that, and later we can let you know. All right, about the comments here. Of course, A to B, so 0 to 1 is a special case. Sure, no problem. And also, if we have a uniform 0 to 1, and if we have a subinterval from S to X plus delta X, and then if we want to find the probability, we want to find the probability. Wait a moment. So if I want to find the probability, you just follow the PDF here, right? Because from 0 to 1. So PDF is 1, label is 1. So we have these. Because of these, so we have the probability, and the probability follows this. So we can use a way with a bit, and then we have the corresponding probability. And it says you can use a way to justify the name uniform. All right, so serve as a reference if you want to know using this way to know why it is the name of a uniform distribution. Okay, so this is the first one, uniform. So up to now, acceptable for you for uniform? Well, if it is okay, let me check the second one. The second one, EXPO, not EXP simply. In fact, the same, exponential. Exponential here, we have a beta. And this beta serves as the mean. All right. So here we have a mean. For exponential, where we can apply. If we want to call interval times or some other times, and then you may have the application of exponential. If we have this parameter, beta serves as mean. Okay, and then the density follow this. 1 over beta multiply exponential raised to the power to minus x over beta. In fact, we have the expression in our supplement using lambda. If we have a lambda equal to 1 over beta, you can rewrite this equation. So you have a lambda and lambda as well, right? So this way, in terms of lambda or the way in terms of beta. Either way, okay for the PDF of exponential. Well, the same. If given PDF, can you have a CDF? So you can check. For exponential, you have the scale parameter beta, even its mean. But this mean it doesn't represent the location. It represents scale parameter. So beta, we have the scale parameter, no shape parameter, no location parameter, only have the scale parameter. All right. If we can check the figure of the exponential, then you can have these. Because not exactly to know where to have the location, so we don't have a location of parameter for exponential. And you can check why and why for variance. As for mode, where to have the maximum 0, so that's why we have a 0 serve as a mode. So look at this one, the largest one, so it's mode. Okay, and also we have beta to check the scale. So we have a beta. All right, so beta, it is mean. So how to have the mean? Using sample mean. So using sample mean to denote beta, and so that we have the estimation, beta hat. So this way, later we can check it is a maximum likelihood estimation for exponential. All right, so up to now, before discussion, the comment. This is the possible aspects of exponential. Is it okay? Okay, so if it is okay, then let us check the comments. The comments here talking about exponential with a parameter beta is a special case of a gamma or variable distribution. When to have these? When alpha equal to 1 for both cases, and then we have the special case for gamma and variable distribution. And later, once we reach gamma and variable, then we can let you know these. All right. And second one, if we have a independent exponential, and how about summation? Summation says exponential plus exponential, but first common, let us have a gamma. And gamma plus gamma, of course, is gamma, right? And because m is an integer, when we have an integer m, then we can have another name called Erlen, m stage Erlen. All right, so that says if we have a gamma, gamma has a special case of exponential and also special case of m stage Erlen. So that says we need to note gamma, and later it's really important to know gamma. And in chapter 4, we already have these. Exponential is the only continuous distribution with the memoryless property. Okay, so you see, in chapter 4, we have an exercise. Actually, I do not assign an exercise, but it is an exercise. If you want to check, you can follow the requirement of the exercise to understand the property, memoryless property. Okay, so let me switch to supplements again. Well, sum of a gamma follows gamma. but we do not change the we do not change the second parameter. So let's check this. But using the supplement, maybe we need to really careful to know how to have the parameter of this. This one, item 4. Item 4 says if we have a gamma, here we have a capital gamma. And gamma first parameter and second parameter. And here the notation is lambda rather than beta. But you should understand beta here is the reciprocal of beta. Lambda here is the reciprocal of beta. Okay, so it says if we have a lambda, so we have the fixed lambda, but we try to gather the parameter for the first position using summation, right? Okay, so it's item 4. So item 4 again, let us check this. Exponential is a special case. So we have this. So exponential, we have this. Follows, I use gamma. Lambda here if I use gamma in supplement. Oh, here, gamma. But we have beta directly. Okay. So either one is okay. Supplement, we have the capital gamma. And right now we have a gamma. GAMMA. So either one is okay, but we have the changes for the second position. Lambda for this one, but beta for the current one. Okay, so I just try to draw your attention to apply the property. So that's why I mentioned this one. Okay, so if we have some independent one, have some, so how to do? So we do not change this. So still have the same lambda. That says still have the same beta, but we need to collect parameter. So right now exponential with the parameter equal to alpha equal to 1. So 1 plus 1 plus we have m. So that's why finally this one follows gamma with the parameter m, common beta. So this one follow the property in supplement 4. Understand me? Okay, that's it. So I just try to let you guys know how to apply the results in supplements. And if you know, then I think you understand the comments. So that's why in chapter 4, I try to provide you the supplements before we discuss the results in chapter 6. Actually, we need them. So that's why I let you know those results. Okay, so that's it. This is the comments for exponential. And of course, here we have a gamma for the code, but we have the special case exponential. And also we have a special case if we have this. And if it is an integer, then we can call alpha stage ln, or m here, m stage ln. All right, so Let's say M stage Erlen or alpha stage Erlen is a special case of gamma as well. Okay, so that's it up now. Is it okay? If it is okay, then we continue. Exponential. Exponential seven times. If you want to model times, you can use exponential. Actually, gamma, the same way, times. Service time, machine repair time, or the other times, we may apply gamma. Okay, as for gamma, I think in supplement, we have the density function for you already. All right, but the same actually that you guys know, current beta with the relationship equal to 1 over beta equal to lambda if you don't like beta. If you like, insist to use lambda, in particular lambda in supplements. All right. So if you have the formula in supplement, you can try to alter these to replace lambda by 1 over beta. Then you will have this formula. You can check. And of course, to define gamma function is necessary. So here we have a gamma function. And gamma function, this one first. Okay, between the equality. And also with the property. And specifically, we have the special results. This one. And also we have the specific results. Okay, and that's all. So if you want to have the density, you need to have some preliminary by using gamma function. And gamma function with the properties. And here you guys should understand k is an integer. So that's why we have a factorial function. All right, so this is a density function. If we want to have the density function, we should understand gamma function. Up to now, is it okay? So you can check, is it true to have the distribution? And here we have a shared parameter alpha. And the beta, similar to exponential, serve as the scale parameter. And we don't have the location parameter specified here. And how about range from 0 to infinity? So we have the half open interval. And you can check, is it true to derive mean variance? Okay, and mod this one. And also we have some of these. Of course, we do not check it because right now we don't have MLE. And this is a curve. How about alpha equal to 1? Exponential. And the others, you see? And also with a parameter not integer. That's it. We may have these. Well, for the mean, I want to check this. Mean, alpha, beta. So here, if we have the distribution, and I demonstrate alpha, beta, the results of alpha, beta for you. Right? From 0 to infinity. So if we have these, we should have this one. right? So this one, the form of gamma, right? And if I want to have the integration, how about this? So right now we can rewrite these. We have a beta again, but right now it is not alpha. It should be alpha plus 1 minus 1. So it's alpha plus 1. So gamma, but here I use this one, gamma. Alpha plus 1. So alpha plus 1, so we need to have this. It should be alpha plus 1. And this one should be alpha plus 1. So you need to rewrite. If we rewrite, then we have this. Rewrite in terms of this alpha plus 1. So we should have alpha plus 1. But move this one outside. Okay. And this one, beta alpha plus 1. So here we need to multiply beta, right? And for this, the same. And the same. If we have this is a form of gamma alpha plus 1 beta. So the whole probability should be 1. So this one, the probability is 1. If it is 1, then don't care about this side. We have these. And also remember what that means. Alpha plus 1 equal to alpha multiply gamma of alpha. So we have alpha and remove. So finally, we have alpha beta for the way to get the expected value. So up to now, I show you this. Understand my idea to derive the result by using the same form of gamma. So for this, is it okay? Acceptable for you? So let me check these results by asking some of you. I'm not so sure. Who inside the Skype? Because I checked my cell phone. So let me casually nominate you guys to let me know your feedback. Okay, so I nominate Haoen. Haoen about the current demonstration about the results for expected value to reach alpha multiply beta. For this discussion, do you understand me? That says, is it okay for you? If it is okay, you just let me have the message and then I will know. So go ahead. Is it okay for you? So are you there, Haoen? Okay, let me call next one. Zongyang, is it okay for you? Okay for you about the derivation to get the expected value? Yes, let me know yes, and no, let me know no. So Songyang, is it okay? Well, no answer. Why? Let me nominate the next one. Chun Hao, okay for you? All right, so I assume okay for you guys because Chunhao let me know okay. I think you just follow this idea for gamma. If you want to derive mean or variance, actually sometimes you can follow the form of the distribution. Why we need to follow the form of the distribution? Because it looks like really complicated. If we can fully utilize the form, and then we may simplify some integral because it is not really easy. So here we follow this idea to have the derivation, even it's really complicated form, but we still can have the results. Okay, just want to let you know this trick. Okay, so to derive these or to derive the others, we have the previous trick. If you can apply the trick, and then I think will be easier for you to have the derivation. For that, I think right now you understand me, right? If so, let's check the comments. First one, I think understand already, right? And second one, by definition, known already, right? And this one, by definition, chi-square with a degree of freedom, we should have these. K over 2, and the second parameter is 2. Here, I just try to draw your attention to our supplement. The same. But second parameter 2, this one is beta. If we want to change it to lambda, we should have a half. So is it true? Let us check these. This one. Right? Chi-square is gamma, and the degree of freedom m. So here we have n over 2, and the second position is lambda, so we have a half. However, if we want to alter a half to beta, then we have 2. So that's why we have these. Beta equal to 2, but lambda equal to a half. All right, so 1, 2, 3 up to now by definition, right? And item 3 by definition identical to the expression in our supplement. Is it okay? And for this one, known in the supplements, right? And this one, by definition, you can try to have the relationship if we have x sub I follows gamma, and then the ratio. Okay, the ratio follows beta. So you can treat this one as the special property. So this one you can treat by the special property, or you can treat this is a definition to get beta. And likewise, this is a special case if you can check. Given gamma and 1 over x, then we can alter x, this one, to y, and y follows Pearson type phi distribution. I think you can check it. As for the 7th item, I think you can check it as well. And that's it. So up to now, this is the comments for gamma. Well, some of the comments follows the description in our supplements. Again, you can fully utilize the results in our supplements, and then I think you can understand more. All right, so this is a supplement. Sorry, this is a comments for gamma. Up to now, is it okay? If it is okay, then let us continue to check. Or you can call whereable. Distribution actually follow the same application scope times. Okay, so this one similar to exponential gamma. So right now we have a different way to have the distribution called whereable distribution. This form. Okay, so as for why this form, I think not really easier to explain, but if you want to know the form, initially you can memorize the form. Just follow the form, and then really easy to have these. And similar to gamma, alpha serves shape, beta serves scale, and etc. We have the others. So for the others, I think I skip it. If you want to check, you can use the property of a gamma function, then you can express mean. Well, we have these results. Think about these. We have these, and also we have these. Do you have any idea about the two? I mean, figures on the left and figures on the right. What is the difference? You understand me? What is the difference? Here, it says if we have a parameter here, all this one we have a passive. Okay, passive skewness. And this one negative. Passive skewness and negative skewness. So where we have the boundary, it says this. Let me check where to have this one. When alpha greater than 3.6, and then we have the negative skewness. Before that one, we have a passive skewness, and that's it. All right, so figures so whereby we have the two categories, passive skewness and negative skewness. Okay, so check the comments. This one, you just treat it as the definition by relating exponential to variable. So how to have this relationship? It's really easy. Setting alpha to 1, and then we have the exponential. And this is a special case, item 2. So you can check. If you want to check how to do. Supplement 1. Apply the technique of supplement 1. Then I think you can understand it is true. So this one you can check. But I want to mention this one, if and only if. What that means, we have two arrows. We need to meet two. Two arrows means left implies right, or right implies left. So for the two, you need to prove separately. If you can prove them separately, and then you can have the results. So 2, you can follow supplement 1 to check these. And 3, I skip it, so you guys can read it. And 2, the same, follow definition. If we have alpha equal to 2, then this distribution is called Rayleigh. And item 5, I think that to you to check. And item 6 is a special observation, so we have these. Alpha lower than 3.6, and then we have a passive skewness. Greater than, then we have a negative skewness. And that's all. So this is the discussion for well-bound distribution. You can look at these. We have two categories. But how about this? No, positive skewness. This one positive skewness. Right? And this one, actually no skewness. The skewness should be 0. Why? Symmetry. So symmetry with 0 skewness. Okay, so after now, I get back to the uniform to that you guys know where we have a positive skewness, where we have a negative skewness. And that's all. So up to now, any questions? If no, right now we can check normal. Normal follow the phone here. In fact, initially you can try to think about if we want to make this one to be a distribution function or a PDF, and then you need to normalize. So here for normalized purpose, and for mu, location parameter, right? And also, how about sigma, scale parameter for compression or for expansion? All right, so that's why for normal we have a location parameter mu and the scale parameter sigma. So distribution, no closed form. So you cannot have any form to represent the CDF. So that's why we simply no closed form. Well, mu sigma square, they can easily map to mean and variance for normal, right? As for mode, well, you can have the largest value, mu. Mu, you will have the largest value. And the others, I think you just follow the current results here to serve us to allow them to serve us the maximum likelihood as method. Okay, so that's all for that. This is normal. And for the discussion of comments for normal, here I go quickly to that you guys know some of those. I think for 1 and 2, you guys check it. Okay, so I skip it. But 3, it is a definition. If we have a 0 and 1, we have a name, standard normal, or called uninormal, right? And this one, by definition, T distribution, right? So 7 and 8, I think you guys can check it. And this one later we will understand, but you can use supplement 1 to know, is it true to have a log normal? Once we reach log normal, we can directly know how to know log normal. Okay, so 5, I think you can use supplement 1 to check, is it true? And these, you can use our proof of a supplement, then you can understand these. If we have a standard normal, and how about reciprocal? And then it follows chi-square. Actually, chi-square degree of freedom 1, and I use notation in all supplement 1. So chi-square and chi-square, actually it's gamma. So if we get sum, so we simply collect all the first parameters. So that's why we have a chi-square of a degree of freedom k. All right, so this one I think you guys can check it. But then you guys know this. Why? Raise the power to 2 follows chi-square 1.5. This one. If we have a 1 here, so this one is 1. Okay, so if we have 1, then this one is chi-square. Right? So you use item 3, then you will have the results. Normal. In particular, talking about standard normal. Raise the power to 2, then we have gamma. Because of standard normal, this gamma also called chi-square of 1. Okay, so because of that, so we have this. So we have this chi-square for O. So chi-square actually is gamma, a half and half. Okay, so sum of O gamma, of course, is gamma again. Right, and here is chi-square of a degree of freedom k. And that's it. So this is item 4. All right, so these are the comments. We need to fully utilize our supplement. So if necessary, you need to refer to our supplement, and then you can understand some of the comments in the table. Is it okay for this? And this is normal, a bell-shaped normal and symmetric one, so 0 skewness. Okay, so that's it. So normal. Well, I forgot that you guys know the application of normal. If we want to talk about normal, sometimes you use model errors, but very likely to describe signal. All right, so how to define signal? You can refer to some communication theory, and then you can understand where to apply normal. But if you apply to signal processing or signal or communication signal, we may have another name, normal to Gaussian. Okay, Gaussian. If you have a Gaussian, actually it is normal. All right, but in that field, we call Gaussian rather than normal. Okay, so this is normal. Is it okay? If it is okay, right now, maybe 1 minute left to take a break. So I think let us take a break right now, and later we can continue to discuss the other possible distribution for the so-called 13 selected distributions of continuous random variable. All right, any question? If no, take a rest again.